Welcome to Maths and Science by IITian channel. In today's lecture, I will be taking up a very good topic of heat and work in thermodynamics. Till now, in the last few lectures, I have discussed about various definitions and introduced you to the various properties of the thermal properties of the working fluid. And a working fluid can be a gas, working fluid can be a vapor, or working fluid can be a liquid. In a thermodynamic system. And some work is done on the working fluid and there will be heat generated. That heat is converted into shaft work or mechanical energy, and that is called as shaft work. From there, from turbine, electricity is generated. That is the ultimate thermodynamic cycle. Or shaft work can also generate movement of the vehicles, rotation of the shafts, mechanical energy. Heat is converted to mechanical energy. That is called as work. And 100% of heat can never be converted to work. There will be some amount of mechanical deficiencies or inefficiencies, irreversibilities in the system. But in ideal cases, we will be considering Carnot cycle, which has the highest efficiency, and also reversible processes. A reversible process will be a continuous process. The working fluid state changes from position 1 to position 2 and the process will be continuous, and in the reverse direction also the process is continuous. And the continuous process diagram will be like this. If it is V volume, if it is P, then from the position 1, state 1 to state 2, if the process is reversible, the diagram will be continuous like this. If process is having irreversibilities, then the process is shown with a dotted lines. That means some irreversibilities are intruded into the system. In the practical sense, there will be always some irreversibilities in the system processes. It is a reversible process. It is an irreversible process. Now, let us define and find out how to calculate the work. To calculate the work done on the fluid, we have one equation in the differential form, dW is equal to P into dV, which can be applied without any reservations in the reversible cycle, irreversible process. In full form, integration form, it is W is equal to integration of P dV, where P is the pressure in pascals, W is the work in joules, work done, V is the volume in cubic meter. Now, let us go into the details of this. When one body at temperature TH is brought in contact with the body at temperature TC. TH is the body at a higher temperature, TC is the body at a cooler temperature or lower temperature, we can even call it as TL. That is up to us. Higher and lower. And heat is when these two bodies are brought together, what happens in the process? Heat transfers from higher temperature to lower temperature body. That heat transfer taking place. This heat transfer stops once both the bodies attain the same temperature. That is equilibrium temperature. That is thermal equilibrium. The equilibrium state of the working fluid or, for example, if we take gas as the working fluid, let us take gas. Body means don't think that only solid body can be brought. A system can be developed in such a way that hot gas and cold gas, they are brought together. Gas is the working fluid, let us say. Let us say as an example. And gas, if it is a working fluid, then under the equilibrium conditions, the equilibrium state, of this gas can be understood by at least two values. A state of a working fluid or state of a gas can be understood at least by two values, specified values, two parameters rather, and the parameters defining the thermal properties. There are various parameters we have discussed in the previous lecture, thermal properties. We will confine ourselves to pressure, volume and temperature and mass. If you use specific volume, what is specific volume? Volume by mass, that is per kg, that means cubic meter per kg. When you use this specific volume, mass is not required because specific volume, you know, volume per unit kg, unit mass, volume per unit mass. And in absolute values, if you want, pressure, volume, temperature and mass, we will confine ourselves to these parameters. In an equilibrium state, or state of a particular working fluid, a state, let us say A, state A, we require at least two properties, two parameters. Let us say we kept the temperature constant. Temperature constant means I am giving only some examples. Temperature constant means isothermal. When temperature is constant, what are the two parameters we require for understanding the state of a fluid such as gas, state of gas? We require pressure and volume. Let us say pressure is on the y-axis and volume is taken on the x-axis, and for isothermal process it will be like this. At a state 1 or state A, it is at state A, this is PA, this is VA. At state B, this is at state B, this is VB and this is PB. Now, it is for a reversible process, as I have told in the beginning. In ideal conditions, we take reversible processes, where we treat that process is continuous. That means there is no break. There are no irreversibilities considered, so that there will be a change in the continuity, or discrete values are not taken, continuous values are taken, so that it can be treated as a continuous function. When the process is reversible, and integration and differentiation is done without any problems. In case of irreversibilities, the values will be changing often, P and V values, and the graph will be broken, and the discontinuities will be more. For our purpose, for our study purpose, we have taken the process as isothermal and reversible. For simplification purpose, when irreversibilities are considered at a higher level of study of thermodynamics, because of the irreversibilities, there will be a inefficiency. What irreversibilities cause? Irreversibilities reduce efficiency of the process. Or cycle. The thermodynamic cycle efficiency will be reduced because of the irreversibility. The irreversibilities may be due to friction in the piston system, piston cylinder system, which I have explained in my previous class. Piston cylinder system. This is the working fluid, gas here. Piston will be moving towards and piston moving away. Irreversibilities reduce the efficiency of the process or cycle, and the irreversibilities due to friction. Can be due to friction between the valves and the piston during the motion. And we are not considering irreversibilities here. We are considering only the process is reversible isothermal process. Reversible isothermal process. It is like and this particular curve is called as at a constant temperature it is isotherm. The PV curve is called as isotherm. System changes in the reversible process. When we consider the reversible process, we can equate it to quasi-static process. Quasi-static process means, for example, when we move something yet with jerks and at rapid speeds, what happens? There will be discontinuities. Like it will be moving like this with high speed, again stopping, moving. This is, it contains irreversibilities. Whereas when a process is very slow, infinitesimally slow, very slow, what happens? We can take a small d of that quantity, dx, and the difference is very small, that from the differentiation principles of definition, when dx is very small, that limit can be estimated or calculated, and differentiation can be continuous. differentiation can be done. This type of process is called as quasi-static. Any process where very slow paced changes do take place is called as quasi-static. From state 1 to state 2 or state A to state B, in reversible isothermal process, temperature is kept constant, hence the variables, the parameters change in the different states. From state A to state B, parameters that change from one state to another are pressure and volume. And the PV diagram, the most important diagram in thermodynamics, this is P, this is V, the PV diagram will be like this. For isothermal, reversible process. Now, this is the PV diagram. Please try to understand again. Very important diagram. And what is the area under this? Curve. The area under this curve, process A to B, A dash, B dash, here we got the insight of reversible isothermal process, and in general the equation of thermodynamics is controlled by the relation between work and heat is controlled by delta Q. This is the heat is equal to internal energy change. Delta is nothing but change into work. Work is PWV, P delta V. This is the equation. Here, pressure is an intensive variable. It doesn't depend upon the size of the system in which it is working. Pressure is force per unit area. It doesn't depend upon the size of the system in pascals. Some pressure is applied means 1 bar pressure is applied, 2 bar pressure is applied, 3 bar pressure is applied, 100 kPa pressure is applied, 200 kPa pressure is applied means that pressure doesn't depend upon the size of the system. And also along with pressure, the other properties which do not depend upon the size of the system are temperature. Temperature also is an example of intensive property, and density. Whereas internal energy, it is extensive property, extensive variable rather, thermodynamic variable. It depends upon the size of the system. Along with internal energy, other variables are which depend upon the size of the system, mass definitely, and volume. Pressure is the intensive variable which doesn't depend upon the size of the system. Volume is the extensive variable which depends upon the size of the system. Because size of the system is more means volume is more. Then what will be the product? Product of an extensive variable into intensive variable is extensive. That means it depends upon the size of the system. That means change in heat is equal to change in internal energy plus work done on the system, work done on the fluid, either gas, liquid, vapor or a mixture. Are you able to understand? This equation is the backbone of all thermodynamic processes. Very important equation. Please keep in mind that change in heat is equal. For that only the work done or the work done by the system or work produced from heat is not fully converted to mechanical energy, and hence heat is a inferior quality of energy. We cannot convert all. For example, I have supplied a heat heat supplied to turbine or any system, heat supplied is, let us say, 100 kilojoules. Then energy produced from turbine during this process, let us say some 60 kilojoules. Efficiency of turbine, energy output by heat supplied into 100, that is 60 by 100 into 100, that is 60%. The turbine efficiency. The total heat supplied to a turbine will not be converted to mechanical energy or shaft work and will not be available to us. If 100 kilojoules is supplied, 100 kilojoules will not be available to us. Something is lost in the process because of the irreversibilities within the system. That's what I have explained here. Reversible and irreversible. In the first slide, reversible and irreversible. This is reversible. This is irreversible. This is reversible. In practical sense, no process is completely reversible. But for simplification purpose, for our study, we take the processes as they work very slowly, the processes happen very slowly, and in a quasi-static manner, that means slowly, very slowly, quasi-static. What is quasi-static? Static means nothing is moving. Quasi-static means it's moving, the process is going on, but at a very slow rate. Please try to understand. Don't get confused with the jargons of the words. Quasi means not full. Quasi. In English, if you say English word quasi is not 100%. Static means static, stationary. That means it is almost near to stationary but not stationary. The process moves very slowly. From state 1 to state 2, like this. Famous PV diagram. From state A to state B, the process is very slow. Quasi-static. Otherwise, the irreversibilities, if the process is fast, if the process is fast, the irreversibilities dominate. Come into effect. When irreversibilities come into effect, discontinuities do happen. Discontinuities do happen in process, and these discontinuities will be represented in a dotted form, and these discontinuities will increase inefficiency in the system, and calculations will become tedious. I am spending this much time on this process. Please try to understand this. A process has to be quasi-static, that means it happens very slowly. The process has to be continuous. The process should not have irreversibilities. Then we can apply mathematical applications such as integration and differentiation. And we can arrive at the formulae such as this. When delta Q is equal to internal energy change plus P delta V, and internal energy is directly related to temperature change. When temperature changes, the internal energy increases. Temperature increases, the internal energy of the system increases. In isothermal process, delta T is equal to 0. When delta T is equal to 0, that implies delta U is equal to 0. Please remember this. There is no temperature change means there is no internal energy change. Very important concept. That implies delta Q is equal to P into delta V. When the process is quasi-static, when the process is continuous, when the process, that particular process curve is differentiable, that function, when the function is, this particular equation is integrable, continuous and quasi-static, what happens? We can write this equation as dq is equal to integral P dV. When there is no change in the internal energy, because we have assumed ideal situations, dq becomes dw, that implies dw. This is ideal situation. Never think that this happens like this. This is ideal situation. dw is integral P dV. That means quasi-static process and continuous process. The process is totally reversible and there are no external agencies to inculcate the irreversibilities. And the temperature is constant. What are the conditions for this? Please, this type of questions do occur in your examination. What are the conditions for dW is equal to integral P dV? One is process to be very slow quasi-static. Temperature difference, that is delta T, is equal to almost 0, infinitesimally small. No external irreversibilities exist in the system. In the piston cylinder, the external irreversibility can be friction. No friction. Etc. Then dW is equal to, we have derived this equation, integral P dV. No, this is W is equal to integral P dV, sorry. It is not dW, W, total. W is equal to integral P dV. If you don't put integral, here let's not put the integral because it is not integral. dW is equal to P dV. Sorry for that. W is equal to integral P dV. No friction. And under these conditions, the isothermal reversible process takes place. We will do one good numerical on this, which has been maybe some questions on this are asked in JEE Advanced and also in JEE Mains. We will do some numerical. Next lecture. And ultimately, the graph for isothermal is like this. This is P, this is V. With this, I want to conclude this lecture, and if you feel there is a value addition because of this lecture to you, kindly hype this video, kindly share this lecture, kindly subscribe to my channel Maths and Science by IITian. With this background, in the next classes onwards, some numericals will start, and also we will talk about the adiabatic process. What is adiabatic? There are 4 types of processes are there. We will talk about them, and we will establish a relation between what you call Cp, Cv and R. We have spoken about isothermal, isobaric, isochoric and adiabatic. Isobaric, isochoric and adiabatic. What happens? Let us see. Ultimately, kindly remember delta Q is equal to delta U plus P delta V. This is the basis for everything. Temperature difference causes change in internal energy. Please remember this. Change in internal energy is not due to kinetic energy, it is due to temperature change. Internal energy is the function of temperature. Please remember this. Best of luck to everybody. Thank you for listening to me. Thank you for viewing my lecture. Please hype, share and subscribe to my channel.